Imagine, if you would, that you live in a really bustling, technologically advanced city.
Okay, like a major metropolis.
Yeah, exactly. Millions of people, towering skyscrapers, automated transit, a totally thriving economy.
Right.
But there is a hidden fatal flaw in the city's design. Every single ounce of your food, your water, the medicine for the hospitals, everything you and your neighbors need to survive, it all comes into the city across a single precarious rope bridge.
Wow, okay. A rope bridge spanning a massive chasm, I'm guessing.
You guessed it, a bottomless chasm.
Okay.
And every single day you look out at that frayed rope and you're just watching the wind whip it back and forth.
That sounds incredibly stressful.
It is, because, with absolute certainty that if that rope snaps, or, if some bad actor decides to stand at the other end and just block it, everything in your city halts.
The lights go out, the shelves empty immediately.
Precisely. You wouldn't just be inconvenienced, you would be looking at a total cascading, catastrophic shutdown of your entire way of life.
Right.
Now, let's strip away the metaphor here. This isn't a dystopian novel we're talking about today.
No, unfortunately it's not.
Right. This is the terrifying everyday reality of our current global energy grid. We are all, you and me and everyone listening, we're all living on the other side of that rope bridge.
It's a really sobering image, honestly. And when you look at the raw data of global logistics, it is completely accurate.
Yeah, the data backs it up entirely.
It perfectly encapsulates just the extreme fragility of the physical systems that underpin modern civilization.
Because we just don't think about it, do we?
We don't. I mean, we flip a switch, the lights come on, we pull up to a pump or a charging station, and the power flows.
Right, it's just magic to most of us.
Exactly. We simply assume the foundational infrastructure beneath that convenience is rock solid. We assume it's engineered with, the same redundancy as a modern data center.
But it's not.
No. As we are about to explore in forensic detail today, the global movement of physical energy is remarkably, almost unacceptably brittle.
And that extreme fragility, that reliance on a few frayed ropes, is exactly what we are dismantling today.
I'm really looking forward to unpacking this.
Me too. For this deep dive, we are pulling from a fascinating, incredibly ambitious 2026 concept document. It's titled Global Energy Corridor System, and they use the acronym GECS, Ultimate Final Master Document.
It's a bold title.
It really is. It's authored by Ollie Hoekerick, an independent researcher specializing in energy security.
Right, and he's brought a totally different perspective to this.
He really has. The mission of our discussion today is to unpack a truly radical new paradigm presented in this text. Hoekerick is essentially drafting a blueprint to tear down the old, outdated, linear concept of energy transport.
The whole brute force method we've used for a century.
Exactly. And in its place, the document proposes what it terms an Internet of Energy.
An Internet of Energy. It's such a compelling phrase.
It is. It's this distributed, multi-route, AI-governed network architecture designed to permanently safeguard global energy security.
Because honestly, if the engineering and the geopolitics behind this concept actually work, it fundamentally changes how the entire physical world operates.
Okay, let's unpack this, because I am so excited about the scale of this. The sheer ambition here is wild.
The scale is massive. We aren't talking about the discovery of a new oil field here.
Right, or like a marginal efficiency gain in a solar panel.
Exactly. Or a new method for fracking natural gas. We're talking about a fundamental structural revolution in how we move the energy we already rely on.
It's purely a logistical and architectural paradigm shift.
But to truly appreciate the necessity of what Hoekerick is proposing, we have to aggressively diagnose the current state of affairs first.
We have to look at the broken system.
Right. We need to look at exactly how and why the single point of failure became the defining characteristic of our modern global economy.
Yeah, before we can even conceptualize an Internet of Energy, we have to understand the dial-up modem reality we are currently operating in.
That's a great way to put it, the dial-up reality.
And the document doesn't mince words about this at all. It points out that the global energy system is entirely dependent on fixed routes that funnel into incredibly narrow, highly vulnerable geographical choke points.
Choke points being the operative word there.
Right, because we tend to think of global trade happening across massive, boundless oceans, wide open spaces.
Yeah, we picture these giant ships just sailing freely. But the physical reality is that these massive supertankers are forced through tiny geological pinch points.
And the text zeroes in on three primary arteries.
Yes.
Yeah.
The Strait of Hormuz, the Suez Canal, and the Malacca Strait.
And we really have to look closely at the physical and geopolitical realities of those specific locations to understand the danger.
Let's take the Strait of Hormuz, for example. The document highlights this with a staggering statistic.
Lay it on us.
That single waterway is responsible for the transit of approximately 20% of the entire global oil trade.
Wait, 20%. 1/5 of the world's oil supply goes through one spot.
1/5, yes. And physically, it gets even crazier. At its narrowest point, the strait is only about 21 miles wide.
Okay, 21 miles sounds like a decent amount of space, though.
It does, until you realize that the actual navigable shipping lanes, the deep water required for these fully loaded supertankers, are only about 2 miles wide in either direction.
Are you kidding me? 2 miles.
Just 2 miles. You have 20% of the lifeblood of the global economy passing through a 2-mile wide lane.
And it's bordered by nations with deeply complex, often hostile geopolitical relationships.
Exactly. The text's central thesis derives directly from this geographic reality. It states, and this is a direct quote, "The issue is not energy production. The issue is energy routing."
Man, that distinction fundamentally shifts the blame, doesn't it?
It completely reframes the problem.
Because we've spent decades, arguably the last century, fighting wars, shifting alliances, and just panicking over who actually owns the energy.
Right, worrying about peak oil or tapping new reserves in the Arctic or wherever.
But this document argues that the energy itself exists in abundance. Production isn't the existential threat at all.
The real Achilles heel is the transit mechanism. Getting it from point A to point B without it getting stuck in a 2-mile wide traffic jam is the actual crisis.
It forces us to rethink the entire conversation around national security.
It really does.
Yeah.
Let's trace the cascading effects of a disruption at one of these choke points, which the text explicitly outlines.
Because it's never just isolated to the energy sector.
Never. First, you have the immediate market reaction, which is oil price spikes. The global commodities market operates on futures and anticipation.
Right, the traders panic.
Exactly. The moment a threat is perceived before a single drop of oil is actually delayed, the price skyrockets.
And then the physical reality sets in.
Yeah. The energy shortages hit countries that rely on continuous just-in-time imports. Their strategic reserves begin to dwindle.
But it doesn't stop at the gas pump. That's the scary part.
Not at all. The next phase is widespread supply chain breakdown. We often forget that petroleum and natural gas are the foundational raw materials for modern manufacturing.
They're in everything.
They're the base components for plastics, fertilizers, pharmaceuticals, synthetic fabrics, you name it.
Which means a blockade in the Strait of Hormuz doesn't just mean your daily commute gets more expensive.
Far from it.
It means agricultural yields drop globally because fertilizer production halts. It means medical supply manufacturing shuts down. It means the plastic packaging required to ship food safely is suddenly completely unavailable.
Exactly. The ultimate consequence, as the document rightly concludes, is massive global economic instability.
It's like every single commuter in a major city being forced to use one single lane of a massive highway. A single fender bender paralyzes millions of people.
That's a perfect analogy. In any basic course on system architecture, whether you are designing a local area network for an office building or, structural supports for a skyscraper, a single point of failure is considered the ultimate engineering sin.
Right, you never designed something to rely on one tiny thread.
Exactly. It means that the destruction or malfunction of one specific, isolated component will bring the entire macro system crashing down.
Yet, astonishingly, we have allowed this exact architectural flaw to serve as the bedrock of global energy logistics.
We really have.
But wait, let me push back on this a bit.
Sure, go ahead.
If we know these 3 choke points are so vulnerable, and we've known about them since, the global oil shocks of the 1970s?
Yeah, at least since then.
Why have we just accepted this structural dependency for so long? Why hasn't a coalition of nations fixed this glaring flaw long before a 2026 concept document suggested it?
It's a great question, and it really comes down to a question of mindset and technological limitations at the time.
How do you mean?
Historically, energy transport was never viewed as a dynamic systems challenge. It was viewed purely as a physical, brute force infrastructure problem.
Oh, I see. Just big, heavy pipes.
Right. Think about how these networks were developed over the 20th century. An energy company finds a viable well. They look at a map, draw the most direct linear path to a deep water port, and they build a massive steel pipe.
Just a straight line from A to B.
Exactly. And once at the port, they load it onto the largest ship physically possible, and that ship takes the shortest maritime line to the destination.
Right.
It was treated as a static engineering problem. The questions were just, how do we build a wider pipe to handle higher pressure, or a longer ship to hold more volume?
It was never conceived of as an intelligent, responsive grid.
Never. We built massive, isolated linear tracks, kind of like the early transcontinental railroads, rather than an interconnected web.
So we've been treating physical commodities fundamentally differently than we treat information.
That's exactly it.
Which naturally leads us to the conceptual leap this document takes. The realization that our vulnerability lies in the routing rather than the supply. It opens up this fascinating thought experiment.
It really does.
What happens if we force physical energy to route around obstacles using the exact same logic that digital data uses?
And this brings us to section 2 of the document, the paradigm shift. The Internet of Energy.
This is where the concept gets really wild.
It radically departs from that century-old brute force engineering mindset. The core conceptual framework of the GECS is that energy is no longer simply transported from point A to point B.
Yeah.
It is dynamically routed.
I want to dissect that phrase dynamically routed because that implies a level of intelligence and responsiveness that physical infrastructure historically just does not possess.
Right. Steel pipes aren't smart.
Exactly. When we think of the traditional pipeline model, the energy inside it is completely blind. 1 million gallons of crude oil moving at high pressure only knows how to move forward through the tube.
That's all it can do.
If there is a rupture or a blockage or a closed valve 300 miles ahead, the oil doesn't know. It keeps moving until it hits the blockage, resulting in a catastrophic pressure event, right?
That is the perfect contrast to what's being proposed. Now, apply the logic of internet architecture to that physical mass.
Okay, let's walk through that.
When you send an email or stream a video, that digital information is broken down into data packets.
Right, little chunks of data.
Exactly. And if a major server hub in Chicago goes offline due to a power outage, the Internet Protocol doesn't just fail to deliver your email and blow up the system.
It routes around it.
It instantly senses the blockage and dynamically routes those data packets through a functioning server in Dallas or Atlanta instead. The end user experiences zero disruption.
And the GECS proposes overlaying that exact digital packet switching framework onto physical commodities.
Yeah, that's the proposal, yes.
But applying the logic of weightless, instantaneous electrons to millions of tons of explosive, viscous liquid, that feels almost like science fiction.
It does sound like it.
When the document says the energy flow becomes aware of its environment, we're talking about a system that possesses the physical sensors to detect a geopolitical conflict 1,000 miles down the line and literally change the geographic direction of the physical mass in real time.
Yes. It diverts the flow into a different pipeline network or triggers loading protocols onto a waiting fleet of ships long before the mass reaches the blockage.
That is mind-blowing.
And that achieves the 3 vital system characteristics the text outlines: redundancy, flexibility, and resilience.
Okay, here's where it gets really interesting for me and where I have a major question.
Go for it.
When I hear new global energy system, I immediately picture a $1 trillion mega pipeline. I picture massive transcontinental boring machines digging new tunnels for decades.
Most people would.
But the text explicitly says the solution is not to replace existing infrastructure. How is that even possible? Are we just slapping a new label on old pipes?
Nah. That skepticism is absolutely warranted, because the history of global infrastructure is littered with failed smart overlays. But the genius of the GECS blueprint lies in its architectural integration.
Integration meaning what exactly?
It's about taking isolated silos of infrastructure and networking them. Think of the current state of global energy like a massive yard filled with hundreds of different disconnected water hoses.
Okay, I'm picturing it.
Some are owned by state oil companies, some by private logistics firms. They operate completely independently.
Right.
The GECS isn't suggesting we throw away those hoses and build one massive, impenetrable aqueduct.
So what does it do?
It proposes building a series of highly advanced intelligent valves, hubs, and sensory relays that physically connect all those separate hoses together into one unified web.
Oh, I see.
You are forcing existing siloed capacity to communicate and share the physical load. If we connect this to the bigger picture, it's about moving from a static infrastructure mindset to a dynamic system architecture.
So the innovation isn't the raw material of transportation, the steel and the ships. It's the connective tissue between them.
Exactly. The intelligence is in the connections.
But Connecting old pipes across international borders to achieve internet-level redundancy that requires more than just a few smart valves. You can't just plug an Ethernet cable into an oil derrick and call it a day.
No, you certainly cannot.
Which brings us to the actual structural blueprint. Let's examine the anatomy of this proposed network.
Let's do it. Section 3 of the document lays out a highly specific 9-layer architecture for the GECS.
9 layers, that's a lot.
It is a comprehensive framework that attempts to flawlessly marry heavy industrial engineering with advanced digital technology. The most effective way to understand these 9 layers is to look at them holistically, much like the human body.
Okay, let's break it down.
The first 6 layers represent the physical infrastructure, the muscle, the bone, and the circulatory system of the network. This is where the physical mass actually resides and moves.
And the top layers.
The top 3 layers represent the autonomous nervous system and the brain, the sensory awareness, the localized reflexes, and the centralized decision-making apparatus.
Let's dissect the physical layers first. The muscle and the bone, layers 1 through 6.
We start with layer 1, the existing infrastructure, the massive primary arteries we already rely on.
Right, the stuff already in the ground.
But the document immediately introduces a critical physical requirement for redundancy in layer 2 parallel pipelines.
Because you need a backup right next door.
Exactly. If we are utilizing existing main routes, the GECS requires physical backups running adjacent to them. If a main line suffers a sudden pressure drop or requires maintenance, the system doesn't shut down the corridor.
It just shifts the flow laterally into the parallel pipe.
Yes, that lateral shift capability is the first line of defense against a single point of failure.
But pipelines, by definition, are geographically fixed. They are rigid. They can't move around a war zone.
Which is why, to achieve true flexibility, Layer 3 heavily integrates liquefied natural gas, or LNG, transport ships as a core physical layer.
Ah, so the ships are part of the network layer.
Yes. In the context of a dynamic network, LNG ships aren't just delivery vehicles. They act as mobile, programmable pipelines.
That's a cool way to think about it. Mobile pipelines.
Right. If a land route is completely compromised, say, an earthquake severs both the main and parallel pipes, the energy can be liquefied at an export terminal and moved across the ocean, entirely bypassing the terrestrial blockage.
And all of this movement, the rigid pipes and the mobile ships, is punctuated by another critical physical layer, the storage facilities. That's layer 4, right?
Yes, layer 4. And this is crucial. In our current linear model, a storage tank is basically a warehouse. It's where fuel sits until someone buys it.
A giant metal bucket.
Exactly. But in a dynamically routed system, storage serves a completely different engineering purpose. It acts as a buffer.
A buffer, like shock absorbers.
Exactly like shock absorbers. The buffer concept is essential for the physics of the system to work.
Because we're talking about massive physical weight.
Right. If you have to suddenly redirect the flow of a massive volume of crude oil, that physical mass has momentum. It has to go somewhere while the new route is being established and valves are changing position.
It can't just instantly stop.
No, it would destroy the pipes. So the storage facilities are integrated directly into the routing hubs to absorb that momentary physical shock, holding the mass temporarily so the continuous upstream flow isn't disrupted.
Okay, so we have the main lines, the parallel backups, the LNG ships acting as flexible patches, and the storage facilities acting as shock absorbers.
And that all culminates in layer 5 and 6, the offshore energy hubs and massive export terminals.
So what does this all mean? It sounds like a 9-layer cake where the bottom is made of heavy steel and liquid natural gas, and the frosting on top is pure artificial intelligence.
That's a very vivid metaphor.
But how do the brains, the top 3 layers, actually physically tell a pipeline to stop and an LNG ship to go? We need to look at the digital layers.
Let's do it. This is where the GECS transitions from a traditional infrastructure project into a cyber-physical system. Layer 7 requires a blanket of digital monitoring systems.
What kind of monitoring?
We are talking about the deployment of millions of industrial Internet of Things, or IoT, sensors.
Millions of them.
Yes. And these aren't simple gauges. These are hardened, high-fidelity sensors embedded inside the pipelines, on the valves, inside the storage tanks, and on the hulls of the LNG ships.
What are they tracking?
They are constantly feeding real-time, microsecond data regarding pressure, temperature, flow rate, viscosity, and GPS location back to a centralized intelligence.
And that centralized intelligence is layer 8, the AI routing system.
Yes, backed by layer 9, which is a massive cybersecurity layer for obvious reasons.
Okay, so if we map this out, we have a system where the bottom layers are thousands of tons of volatile commodities moving at high speed, and the top layer is an artificial intelligence crunching data.
That's the architecture.
But bridging that gap is where I still stumble. It's one thing for an AI to decide a route needs to change based on sensor data. It's another thing entirely for that AI to actually physically execute the change.
Right. How does the digital brain physically command the analog muscle?
Exactly. How does it turn the wheel?
It requires complete integration into the industrial control systems and SCADA networks of the physical infrastructure.
So the AI has direct control of the hardware.
Complete control. When the AI determines a route deviation is required, it doesn't alert a human operator to go turn a heavy wheel. It electronically interfaces with massive automated actuator valves.
It turns the valve itself.
Instantly, it systematically begins closing the flow to the compromised route while simultaneously opening valves to the storage buffers to handle the back pressure.
And what about the ships?
At the exact same moment, it transmits automated encrypted dispatch coordinates to the LNG fleet, rerouting ships in transit to new export terminals to pick up the diverted flow. It is a highly synchronized ballet of heavy machinery, entirely automated to operate faster than human reaction time.
It's literally an autonomous nervous system for global logistics.
That's the goal.
I mean, when you touch a hot stove, your brain pulls your hand away before you even consciously register the pain.
Exactly.
The GECS is designed to pull the oil away from a geopolitical conflict before the global markets even register the threat.
Precisely.
It's brilliant in isolation, but we need to zoom out a bit. Where is all this physical infrastructure actually located?
The geography is just as important as the technology.
Right. If we are avoiding Hormuz, Suez, and Malacca, where are the new arteries? The text outlines what it calls the three-corridor model.
Yes. The macrogeography of the GECS is designed specifically to neutralize those historical choke points. It proposes 3 primary, massive corridors originating from the major production centers in the Gulf.
Let's trace them. What's the first one?
First, there is the North Corridor. This is an overland route taking energy from the Gulf, moving it north through Iraq, into Turkey, and ultimately feeding into the European energy grid.
Okay, so that's the European artery. And the second?
Then we have the West Corridor. This also originates in the Gulf, but moves laterally across the Arabian Peninsula. It traverses Saudi Arabia overland and terminates at export hubs on the Red Sea, granting immediate maritime access to global markets.
Bypassing the Strait of Hormuz completely.
Completely. And finally, the South Corridor, which routes energy from the Gulf down through the United Arab Emirates and Oman, again bypassing the straits entirely to access the open ocean, primarily to feed the massive demand centers in Asia.
Okay, when you look at these 3 corridors on a map, the strategic value becomes immediately apparent. You are taking the world's most vital commodity out of the vulnerable 2-mile-wide waterways and moving it overland across massive sovereign territories.
With a huge geographical shift.
A blockade in the Strait of Hormuz becomes physically irrelevant if the oil is flowing overland through Saudi Arabia to the Red Sea or through Oman to the Arabian Sea.
Exactly. It defangs the threat.
But the foundational principle of the GECS is not just that these are 3 separate, safer options. The document explicitly mandates, quote, "These corridors are not independent. They are interconnected and dynamically managed."
And that interconnectedness is the key to the whole system.
Let's think through the logistics of that. Say 1 million barrels of oil are moving up the North Corridor, traveling through pipelines in Turkey destined for Germany.
Okay.
Suddenly, a massive unforeseen disruption occurs. A catastrophic earthquake severs the primary and parallel lines, or a sudden regional conflict makes the airspace above the pipeline too dangerous for operation.
A total halt.
Yeah. What does it actually mean for the system to dynamically shift that specific volume of oil to the West Corridor?
It means the architecture operates as a true web, not just parallel tracks. When the North Corridor is compromised, the AI doesn't just issue a halt command to the origin of wells in the Gulf.
It doesn't just turn off the tap.
No. It instantaneously calculates the available capacity in the West Corridor pipelines across Saudi Arabia and the South Corridor pipelines through Oman.
It looks for alternative paths.
Right. And it triggers the storage buffers at the origin points to hold the excess flow for the few hours it takes to physically reverse or laterally shift the flow through connecting infrastructure. It redirects that exact volume toward the Red Sea or the open ocean instead.
Okay, I have to stop you there and push back on the physics and geography of this.
Go ahead.
I understand the concept of a web, but we are talking about continental scale distances here. It's like having three massive interstate highways leaving a city, Interstate North, West, and South.
Sure.
If I'm driving my car on Interstate North and there's a massive crash that blocks all lanes, I can't just magically teleport my car over to Interstate West. I am stuck in the traffic jam.
Right, you're trapped.
The corridors in the document are separated by hundreds, sometimes thousands of miles of desert and mountains. How do you physically link them so that the oil doesn't just hit a dead end?
This raises an important question, and it's the ultimate engineering challenge of the proposal. Your highway analogy highlights exactly why a traditional pipeline network fails.
Because there are no exits.
Exactly. To make your analogy fit the GECS model, you have to imagine that miles before you ever reach the pileup on Interstate North, your car's autonomous driving system communicated with a central traffic AI.
Okay.
That AI knew about the crash instantly and seamlessly routed you onto a massive high-speed interchange that connected directly to Interstate West. You bypass the blockage entirely without ever tapping the brakes.
Oh, I see. A centralized interchange.
In the GECS architecture, you need a physical interchange. You need a central node that connects the disparate geographic corridors.
And that leads us to Section 5. To bridge the gap between these massive geographical corridors, you need a hub that acts as the grand conductor of this energy orchestra.
Yes, the brain of the operation.
The text identifies this as the offshore energy router.
This is the core innovation of the entire blueprint. At the very center of this massive geographical web sits the offshore main energy hub.
And it functions literally as a router.
It is the physical and digital nexus of the GECS. The document is very clear that this hub functions exactly like a routing center in a digital network.
Which means what, physically?
It is the grand interchange. It is the facility where the high-capacity pipelines, the LNG dispatch terminals, the massive storage buffers, and the AI control systems all physically intersect.
I just want to dwell on a specific sentence from the text for a moment because it is so conceptually dense. It says it operates similarly to an internet data router. Instead of data, it routes energy.
An internet router for physical mass.
An internet router for millions of tons of explosive liquid. It's wild.
It's a profound, almost dizzying concept. And to understand how it functions, we have to look at the dynamic routing logic, the actual algorithms that govern the AI's decision-making inside this router.
Because the AI isn't just reacting to broken pipes, right?
No, it is a predictive analytical engine. The document outlines 5 highly specific, real-time parameters that dictate every single routing decision.
Let's hear them.
First, geopolitical risk. Second, supply disruptions. Third, demand changes. Fourth, infrastructure capacity. And fifth, transportation costs.
Let's run a simulation of what it looks like when an artificial intelligence is crunching those 5 variables in milliseconds. Let's take the first one, geopolitical risk.
Okay.
This AI must be continuously scraping global news feeds, satellite imagery of military deployments, maritime transponder data, even diplomatic channels.
Absolutely. It's ingesting all of it.
If a nation begins amassing naval vessels near a shipping lane, the risk score spikes.
And it preemptively alters the route. Now take the second, supply disruptions. It's reading those millions of IoT sensors for sudden pressure drops or mechanical wear and tear.
It knows a pipe is about to break before it breaks.
Exactly. Then the third variable, demand changes. It's analyzing weather patterns globally.
Wait, weather patterns?
Yes. If it detects a sudden, severe cold snap forming over northern Europe, it knows the demand for natural gas is about to exponentially increase in that specific region, so it proactively shifts routing priorities toward the North Corridor.
Wow. And it balances those external factors against internal system realities, right?
Yes, which is the fourth variable, infrastructure capacity. It knows, down to the gallon, exactly how much room is left in the storage buffers in Oman versus the export terminals on the Red Sea.
And finally, transportation costs.
Right. The AI is constantly running economic optimization models. It's analyzing current maritime shipping rates, pipeline tariff costs, and energy expenditures required for liquefaction.
So it's finding the cheapest route, too.
Yes, ensuring the diverted route is not just physically viable, but economically optimal. It synthesizes all 5 variables, constantly adjusting the physical flow of millions of barrels of oil to navigate the safest, cheapest, most efficient path to the consumer.
Let me make sure I'm wrapping my head around this. If I'm an internet router, I'm just redirecting electrons. It's instantaneous. But here we are talking about moving physical mass.
Heavy, dangerous mass.
Right. Earlier, we talked about the danger of abruptly stopping flow. There is a phenomenon in fluid dynamics known as the water hammer effect.
Yes. The water
If
hammer.
you have a massive volume of liquid, say, heavy crude oil in a 3-foot diameter steel pipeline moving at high velocity, it possesses immense kinetic energy.
Unimaginable kinetic energy.
If an AI suddenly slams a massive automated valve shut to reroute it, that kinetic energy has nowhere to go. It creates a massive shock wave that travels back up the pipe, and it will literally shatter the steel.
It would cause a catastrophic rupture, yes.
So how does a system automatically redirect physical mass without the whole thing coming to a grinding, catastrophic halt due to its own inertia?
That physical reality is precisely why the Internet of Energy could not have been built 20 years ago, and why the integration of those 9 layers is non-negotiable.
It's a physics problem.
Exactly. The system cannot and does not just slam valves shut. The entire architecture is built around a mantra explicitly stated in the text. The system does not stop. The system reroutes.
Okay, but how?
To overcome the water hammer effect and manage the immense inertia of the fluid, the offshore energy router utilizes the storage facilities and the LNG plants as massive, highly engineered physical buffers.
Let's explain that buffer mechanism, because when I think of a buffer, I think of streaming a 4K video online.
That's a great comparison.
If my internet connection momentarily drops, the video doesn't immediately freeze. It keeps playing for a few seconds because my device downloaded a buffer, a temporary stockpile of data ahead of time. Are we talking about the same concept, but with millions of gallons of fuel?
Conceptually, yes, but mechanically it works in reverse to absorb the shock.
In reverse. How so?
Imagine the AI decides to shift a massive flow of oil from the north corridor to the west corridor due to a sudden geopolitical threat. It doesn't close the north valve and then open the west valve.
That would cause the water hammer.
Right. Instead, it slowly opens a massive diversion valve leading into a localized high-capacity storage facility, the buffer.
Okay, so it gives the oil somewhere to go.
Yes. As the diversion valve opens, the primary valve slowly constricts. The immense kinetic energy and momentum of the oil flow safely into the massive storage tanks, dissipating the pressure safely.
It just absorbs the energy.
The system never physically stops the upstream flow. It merely gives the momentum a safe place to go.
And then what? It just sits there.
No. Once the kinetic energy is absorbed and the flow is stabilized within the buffer, secondary pumps slowly introduce the oil into the West Corridor's pipeline network, or pipe it directly into waiting LNG ships.
That completely demystifies the engineering for me. The buffer entirely negates the water hammer effect, ensuring the continuous flow of energy that the global economy demands.
The storage tanks aren't warehouses. They are the physical shock absorbers for the entire global network.
The theory's brilliant and the logic is sound.
Yeah.
But to truly understand if the GECS is viable, we need to put it through a stress test.
We need to see how it handles a global crisis.
Exactly. A blueprint is just paper until you build it and break it. Let's look at Section 6, the crisis response model.
The author clearly anticipated that need. The document doesn't just offer vague assurances, it outlines highly specific scenarios to demonstrate step-by-step how the architecture responds under extreme duress.
Okay, let's put the system through its paces. Scenario 1. This is the nightmare scenario that keeps defense secretaries awake at night. The total closure of the Strait of Hormuz.
The ultimate stress test.
Walk me through it.
Okay.
Imagine the scenario. It's Tuesday morning. You wake up, check your phone, and every news outlet is flashing the same alert. Strait of Hormuz blocked. Hostile actors have mined the waterway and fired on commercial shipping.
In our current reality, the fallout is instantaneous.
Right. Global markets plunge into freefall before the New York Stock Exchange even opens. The price of a barrel of crude doubles, then triples. Logistics companies declare force majeure. It is the snapping of the rope bridge.
Total chaos.
So what happens in the GECS reality?
In the reality governed by the GECS, that geopolitical panic is almost entirely neutralized by automated physics-based redundancy.
Neutralized? How?
The text outlines the system's immediate reflex. Energy redirected via Red Sea and Turkey. Let's break down the timeline. The moment the IoT monitoring systems detect a halt in maritime traffic, or the AI's risk assessment algorithm registers the military escalation via satellite data, the offshore energy router takes command.
It takes over immediately.
Milliseconds. The massive volume of oil being pumped out of the Gulf, originally destined for supertankers waiting in the now-closed strait, is instantaneously diverted into the massive physical buffers.
It opens those diversion valves.
Yes. Over the next few hours, the automated valves shift the immense flow away from the coast. It is pushed forcefully into the overland pipelines of the West Corridor, traversing Saudi Arabia to reach the safety of the Red Sea, and simultaneously pushed up the North Corridor toward Turkey.
Okay, but what about the physical ships? You have a fleet of supertankers that were en route to Hormuz that now have literally nowhere to dock.
The digital layer handles them simultaneously. The AI transmits new navigational coordinates to the autonomous navigation systems of the waiting LNG and crude fleets.
It just reroutes the ships?
It orders them to bypass the Gulf entirely, routing them to the export terminals on the Red Sea and the Mediterranean to pick up the redirected flow.
Wow.
From the perspective of an end consumer in Tokyo or Berlin, the crisis is invisible. The energy shipment arrives via a slightly different route, perhaps a day later. But the catastrophic supply shock and the subsequent economic panic never materializes.
That is an astonishing level of geopolitical insulation.
It changes the world order.
Let's escalate to scenario 2, a Red Sea disruption.
Okay.
We know from recent history how vulnerable the Red Sea and the Suez Canal approach are to asymmetrical warfare or even just, a badly piloted container ship.
The Ever Given all over again.
Right. Historically, that sends shockwaves through global markets immediately. You're telling me the system just smoothly shifts the load. If the West Corridor's maritime access is suddenly cut off, what is the system's countermove?
The text provides the exact protocol. Energy redirected via Turkey and Oman. Again, the system relies on the interconnected web.
How does it balance it?
If the Red Sea access is compromised, the offshore energy router calculates the lost capacity. It pushes the North Corridor through Turkey to its absolute maximum safe operational pressure.
Ramping up the northern route.
Yes, and simultaneously, it diverts the remaining displaced volume southward. It forces the energy through the South Corridor pipelines traversing the UAE and Oman to reach export terminals on the Arabian Sea, granting direct access to the open ocean and completely bypassing the Red Sea bottleneck.
Okay, I have to pause and process the scale of what you're describing.
It's massive.
You're suggesting that if a major global shipping artery is shut down by a conflict, this AI-driven network simply shifts millions of barrels of physical mass across the Arabian Peninsula to Oman, and the end consumer barely notices. No massive price spikes.
That is the exact promise of the GECS. The market doesn't panic because the foundational cause of the panic, the actual cessation of energy flow, never occurs.
Because the AI is already handling it.
What's fascinating here is that the crisis response is automated. By the time the news anchors are reporting the disruption, the AI routing systems in Layer 8 have already executed the bypass.
The valves have shifted.
The storage buffers have absorbed the transition shock, and the fleets have new headings. The flow of energy merely changed its path. It never stopped.
It's essentially the physical manifestation of internet censorship circumvention. When a firewall blocks a website, a VPN routes your connection through a different country.
A physical VPN, that's a great analogy.
The GECS is a physical VPN for the global economy.
It really is.
Let's look at scenario 3. This one is less about geopolitics and more about raw engineering failure, a catastrophic pipeline rupture.
Okay, a purely physical break.
Yeah. Let's say a massive, unprecedented earthquake strikes a remote region along North Corridor, violently severing a main pipeline.
This scenario perfectly highlights why the multi-layer physical architecture is non-negotiable.
Walk us through it.
The document details the automated response. LNG and storage systems activated. In the microseconds following the rupture, the IoT pressure sensors detect the catastrophic drop.
Because the pressure vanishes.
Right. The AI instantly seals the automated shutoff valves immediately upstream and downstream of the break, isolating the damage and preventing a massive environmental disaster.
But the upstream oil is still flowing toward the break.
Yes. First, the AI attempts to shift the flow into the parallel pipeline layer 2. But if the earthquake severed both the main and the backup lines, the system escalates.
It hits a physical dead end.
Exactly. And that is when the intelligence of the network activates Layer 3 and Layer 4. The upstream energy is immediately diverted into regional storage buffer facilities.
The shock absorbers again.
Concurrently, the AI dispatches the fleet of LNG ships and coastal tankers to the nearest functional export terminals upstream of the rupture.
To pick up the stranded oil.
Yes. The ships take on the load, physically bridging the gap over the ocean or along the coast, entirely bypassing the ruined terrestrial infrastructure and delivering the energy to functioning ports downstream of the damage.
So the ships act as a temporary pipe.
Exactly. As the text emphatically concludes regarding this multi-layered redundancy, This ensures continuous energy flow under all conditions.
Continuous energy flow under all conditions. That is the holy grail of global logistics.
It really is.
It sounds like a beautifully engineered sci-fi utopia for logistics, but a blueprint is just paper until you build it. Taking an incredibly entrenched, politically fraught, century-old global infrastructure and transforming it into a synchronized, AI-governed web seems like the kind of mega project that would require 50 years.
And endless United Nations debates.
Right, and more capital than exists in the global economy. How long does a global overhaul like this actually take, according to Huckerek?
This brings us to Section 7, the implementation roadmap, and it contains perhaps the most shocking claim in the entire document.
Bruce.
This is not presented as a multi-generational 50-year plan. The text outlines a staggering 36-month timeline.
Wait, 36 months?
3 years, yes.
A 36-month timeline to build an internet of energy? I know people who have taken 36 months just to remodel their kitchen. Is this timeline actually realistic, or is this the ultimate best-case scenario?
It's incredibly aggressive. It's broken down into 3 phases.
Let's hear them.
Phase 1 is months 0 through 6. The stated goal is to optimize existing infrastructure.
6 months to optimize the globe. Okay, phase 2.
Phase 2 is months 6 through 18. The goal is to expand parallel capacity in LNG systems.
And phase 3.
Phase 3 is months 18 through 36. The goal is full integration and AI routing.
And the outcome.
The expected outcome at the end of year 3 is a 70 to 80% reduction in choke point dependency.
That timeline sounds completely detached from reality. Let's critically analyze this. 3 years to revolutionize the global energy grid. Why does he think phase 1 optimization can happen so quickly?
Well, let's look at the logic. The reason phase 1 can theoretically occur in just 6 months reinforces the core philosophy of the entire system. It relies heavily on existing infrastructure.
Because we aren't starting from scratch.
Exactly. We're not spending a decade dealing with environmental impact studies, surveying land, and digging thousands of miles of new trenches. The heavy steel is mostly in the ground already. The deep water ports already exist.
So what are we doing for 6 months?
Phase 1 is essentially a massive synchronized audit. It's about standardizing communication protocols across different national grids and beginning the installation of the IoT sensor layer across disparate systems.
Okay, so phase 1 is basically a global IT audit and a massive sensor installation project. It's complex, but it's not pouring concrete.
Precisely. Now, phase 2 does require heavy physical expansion, laying the required parallel pipelines in critical zones for redundancy, expanding the storage buffers, and rapidly scaling up the construction of LNG vessels.
Allocating 12 months for that seems wild.
It is incredibly aggressive. It would require wartime levels of industrial mobilization. But from a pure engineering standpoint, if the capital is unleashed, it is technically feasible.
But phase 3 months, 18 through 36, that's where the true transformation occurs, right? Full integration and AI routing.
Yes. It's a software and integration challenge more than a pure construction challenge. This phase transforms energy from a static infrastructure into a dynamic network.
I'm going to push back incredibly hard on this, not from an engineering perspective, but from a human reality perspective.
I thought you might.
Software integration. You are talking about getting the state-owned oil companies of Iraq, the pipeline operators of Turkey, the royal energy ministries of Saudi Arabia, and the highly regulated utility grids of the European Union to all agree on a unified data protocol.
It's a diplomatic nightmare.
It really is. Furthermore, you are asking sovereign nations to hand over the physical manual override controls of their most vital national security assets to a centralized autonomous AI housed in an offshore router.
Right, you're asking them to give up control.
That isn't an IT challenge. That is the greatest diplomatic hurdle in modern history. Will nations actually surrender that level of sovereignty?
I validate your skepticism completely. That is the most salient critique of the entire proposal. You have identified the massive geopolitical friction inherent in the system.
Because it's asking for a utopia.
To validate the 36-month timeline, one has to assume an unprecedented, almost utopian level of international cooperation, likely driven by the mutual terror of a catastrophic choke point failure.
The fear has to outweigh the pride.
Exactly. The engineering timeline, building the brain and connecting the nerves, is mathematically possible in 3 years. But overcoming the sovereignty issues, convincing nations to trust a black box AI with their economic survival, is a monumental task that the document just sort of glosses over with the phrase full integration.
And that leads to an even deeper geopolitical implication. Let's look at the strategic impact section of the document.
The outcomes of the system.
Right. What does a world with a 70 to 80% reduction in choke point dependency actually look like? The text lists four primary outcomes.
1. Reduces global energy risk. 2. Stabilizes energy markets. 3. Improves supply chain resilience. And 4. Decreases geopolitical vulnerability.
Let's really analyze that fourth point, decreasing geopolitical vulnerability, because it represents a tectonic shift in global power dynamics.
It fundamentally changes global diplomacy.
We've talked about how this system bypasses choke points to ensure energy security for the consumer nations, but what about the nations that actually control those choke points?
That is the uncomfortable truth at the heart of the GECS. While the document presents the decrease in geopolitical vulnerability as a pure, stabilizing global good, it is effectively stripping immense power away from specific actors.
Because if a choke point can no longer be used as a weapon, how does global diplomacy shift?
Drastically. If you are the nation that controls the territory bordering the Strait of Hormuz, or the government that operates the Suez Canal, your control over that narrow geographic space is your primary strategic deterrent.
It's your trump card.
It is your leverage on the global stage. Your ability to threaten to close that strait is what forces superpowers to negotiate with you. It's what secures foreign aid, military concessions, and diplomatic immunity.
Exactly. But if this Internet of Energy comes online and suddenly a threat to close a choke point doesn't trigger a global economic panic, but merely triggers a silent rerouting protocol by an AI in an offshore hub, that leverage completely evaporates.
The leverage is reduced to zero. By neutralizing the geography, the GECS neutralizes the geopolitical weapon.
That's massive.
We have to assume that the nations whose power relies on the fragility of the current system would view the implementation of this dynamic network not as a technological miracle, but as a direct threat to their national security and influence.
They would fight it every step of the way.
They would likely resist its integration fiercely. The GECS transfers power from those who control geographic bottlenecks to those who control the resilient, distributed network.
It is a profound realization. You are using the logic of the digital world to fundamentally rewrite the power structures of the physical world.
That's exactly what it is.
What an incredibly dense, thought-provoking journey this concept document has taken us on. Let's take a breath and briefly recap the vast territory we've covered today.
We've covered a lot of ground.
We started by diagnosing the terrifying fragility of our current reality, the realization that 20% of the global economy is squeezed through a 2-mile-wide lane in the Strait of Hormuz, creating a single point of failure that threatens cascading global collapse.
And from that grim diagnosis, we explored Hokerek's proposed paradigm shift, the Internet of Energy. We moved away from the century-old mindset of brute force, linear engineering, and embraced the concept of dynamically routing physical mass.
Much like we route data packets across the web.
Exactly. We examined the 9-layer anatomy of this network, understanding how the physical muscles, the pipelines, LNG ships, and storage buffers integrate with the digital brain of IoT sensors and AI.
And we mapped out the 3 massive arteries, the north, west, and south corridors that allow the energy to physically bypass the globe's worst choke points by traveling overland.
And we delved into the physics and the algorithms of the offshore energy router.
Right, marveling at how a centralized intelligence can manage the immense kinetic energy of moving oil, using visible buffers to execute seamless route changes without shattering the infrastructure.
To truly encapsulate the sheer ambition and the defiant engineering philosophy of this blueprint, I think it is necessary to read the final statement of the document verbatim.
Please do.
It reads less like an academic conclusion and more like a manifesto for the future of global logistics. Hokerek writes, "This is not a pipeline project. This is not a regional infrastructure plan. This is a global system architecture. This is the Internet of Energy. This system does not stop. The system reroutes."
The system does not stop, the system reroutes. That is a powerful organizing principle for the future.
It really is.
It's been an absolutely mind-expanding deep dive into the blueprint of tomorrow's physical world. But before we wrap up, I want to leave you, the listener, with a final provocative thought experiment to ponder.
I love a good thought experiment.
We've spent this entire deep dive exploring how applying digital network logic, the resilient architecture of the internet, to physical oil and gas can eliminate global choke points and secure the energy grid. But if this Internet of Energy routing model is actually achievable, what other incredibly fragile physical supply chains could be completely reimagined using this exact same blueprint?
Oh, that's an interesting question.
Think about the global food supply. It is heavily reliant on a few major shipping lanes, specific rail networks, and concentrated fertilizer production
Which
hubs.
are also vulnerable to choke points.
Exactly. Or think about the rare earth minerals required to build the microchips in the phone or the computer you are listening to this on right now.
Also highly concentrated.
If human engineering has reached a point where we can successfully dynamically route massive physical commodities like millions of barrels of crude oil in real time, relying on AI and physical buffer systems, are we on the verge of an Internet of Everything physical?
Wow.
Could this architectural mindset, if applied broadly, effectively end catastrophic supply chain shortages forever? Imagine a world where the rope bridge never truly snaps, because the millisecond it begins to fray, the network has already built you another path. Thank you so much for joining us on this deep dive into the architecture of resilience.